Hi guys, welcome to the video for Electrochem, right? So let's do a summary on this. This is the learning outcome. So first, you must able to recognize redox reactions, oxidation number calculations. So you need to identify which species is being reduced, which species is being oxidized based on the oxidation number. Okay, next is able to understand and describe an electrolytic cell or electrolysis process. Next, you must be able to write out half equations and overall equations for the redox reaction that take place. The last one is to use Faraday's law to perform calculations in an electrolytic cell. Okay, so these are the learning outcomes that you need to achieve at the end of this week. All right, redox processes. So what is that redox? Redox is actually two different reactions, redox, so reductions and oxidations. Okay, so it can read as red for reductions, ox is for oxidations, and these two reactions must occur simultaneously. Okay, and what is that oxidizing agent? Oxidizing agent is a species or a reactant that causes oxidation and itself gets reduced. Okay, so on the opposite side, reducing agent is a reactant that causes reduction, because I said reducing agent is an agent that causes reductions and itself must be oxidized. Okay, so like in the diagram shown here, you can see a reducing agent will causes a reductions and itself must be oxidized. How to oxidize this? It donates an electrons to the Y. So Y will accept the electron, therefore it gets reduced. So at the same time, if you look at this oxidizing agent, itself must get reduced, and at the same time, it oxidizes the X. Okay, so they are working together. One is donating electrons, one is accepting electrons. All right, so that's redox, and must able to identify differentiates between oxidizing agent and reducing agent. Now, sometimes in the questions, they tends to put it as oxidant and reductant. Okay, oxidant is actually same as oxidizing agent. Reductant is the same as reducing agent, just slightly different terms used. All right. Next, we look at these examples of redox reactions. Now we can see from here, we check one by one. Zinc is supposed to be a solid. When zinc under its elemental state, the oxidation numbers or the charge is always 0. Okay, and then at the end of the reaction, it changes into 2 positive, which means it gets oxidized. When the oxidation number increases, getting more and more positive means it is losing electrons. Okay, it is losing electron, hence we call this as oxidation. Okay, and initially we have copper 2 plus. At the end, it changes into copper solid. Like I said, elemental state is always 0 in oxidation numbers. So from 2 positive becoming 0 means decrease in oxidation numbers. So we call this as reduction. All right, so which one is the oxidizing agent? Which one is the reducing agent? Is stated here. Now, very simple. Zinc undergoes oxidation. Therefore, zinc is a reducing agent, because it undergoes oxidation, which is the opposite. Now, copper 2 plus undergoes reduction, which means copper 2 plus is an oxidizing agent because itself reduced to copper solid. Okay, so this is how we identify redox reactions. Now, next one, this is something new, guys. Disproportionations. Now, what is that disproportionation? It is still redox reaction, but just that reductions and oxidations is occurring on the same substance or species or element. All right, you get that? Now, for example, in this, the previous example, zinc is a reducing agent, copper 2 plus is an oxidizing agent, and then each of these will undergo different reaction, oxidation and reductions, right? Now, for these proportionations, one species undergoes both reactions at the same time. So you're getting 2 different products. Now look at the examples given here. Initially, I can see from here, the oxidation state of copper is positive 1. All right, and then it turns into a copper solid, which is 0. So what reaction is this from positive 1 to 0? Reduction, right? And from the same compound here, positive 1, it started with positive 1 copper oxide, it turns into it turns into copper sulfate, which is 2 plus here in terms of its oxidation numbers. So what does it mean? Copper from +1 undergoes reduction to form 0, undergoes oxidation to form 2 plus. So the same element, copper, okay, undergoes oxidation and reductions together, forming two different products here. And this is what we call a disproportionation reactions. All right, so I can give you another example. So let's say I have this structure, sodium hydroxide plus chlorine gas turns into sodium chloride plus NaClO plus water. Okay, and then we try to balance the equations. 2 NaOH, chlorine you have 2, 2O, and then you have H2. Yes, that's balanced, right? Now, can you try to check whether this equation is showing a disproportionation reactions or just a normal redox reactions? Now, very simple. How to identify that? If you see an element appear twice in a product side, then most probably it is disproportionation. For example, I have chlorine here, and it appeared chlorine in two different compounds. See that? Chlorine appear in two different products from one single chlorine gas. Okay, let's check. What is the oxidation number of chlorine here in terms of its elemental state? It's always 0. And what is the oxidation of chlorine here? Na is positive, hence Cl is -1. So what happened from 0 to -1? It decreased, right? So it decreases means it is reduction. All right, there's another chlorine here in NaClO. Now, what is the charge of chlorine in this compound? Na is positive, oxygen is 2 minus. So what is the charge of chlorine? Very simple. Now, the simple way to do that is sodium is plus, so +1. All right, add up with chlorine, which is unknown, we are calculating it, plus with -2 equals to, what is the overall charge for this compound? 0, because it's balanced out the charge, so equals to 0. And from here we can see chlorine is actually +1. So the charge of chlorine here is +1. Hence, from 0 to +1, then this is actually an oxidation reactions. See that? From a single element of chlorine, it undergoes oxidation as well as reductions, forming two different products. So this is what we call a disproportionation reactions. All right. Now, rules for working out oxidation numbers. Now, very simple. The first rule is all three atoms in elemental state actually with an oxidation number of 0. Like I mentioned, magnesium is supposed to be a solid, so magnesium is 0. Iron is a solid as well. Under solid state, it is 0. Oxygen is a gas, O2 gas, 0. Chlorine is a gas, Cl2, 0. So these are the oxidation numbers for element, is always 0. Now, for simple ions, the charge of the ion is actually the oxidation numbers. For example, sodium is from group 1. All right, so it's +1. That's the charge, which is also the oxidation numbers. Aluminium is from group 3 or group 13. Therefore, you get 3 plus, and that is actually the oxidation numbers. And for magnesium is from group 2. Therefore, 2 positive charge, and that's the oxidation numbers. For simple ion is very simple. What if you have this? What is the oxidation number of chlorine minus? Of course, -1. Okay, that's for simple ions. Now, for covalent compound, all right, for covalent compound, because usually covalent compounds form by sharing of electrons, right? So it is not by forming ions. So it's a bit weird for us to assume that in a covalent molecule, we have a positive and negative charge. And then how do we actually identify the oxidation numbers for a covalent molecule? We still have to make assumption on this. The bonded electrons are on the more electronegative atoms. Like we learned this, more electronegativity. Okay, so the oxidation numbers are the charge on the ions, so-called the ions, which means, for example, I have HCl here. So even though HCl is a covalent molecule, but we're still able to identify the oxidation numbers. The electrons here is moving towards chlorine. So chlorine will be the negative. Okay, hydrogen will be the positive. So chlorine here, what is the oxidation number of chlorine? -1. What is the oxidation number of hydrogen? +1. although we know that the negative and positive here in terms of bonding is just a delta positive and negative. But in terms of redox, we still have to assume that hydrogen is having a positive 1 charge, chlorine is having a negative 1 oxidation numbers. Okay, same goes to these guys. SO3, right? So in terms of SO3, let's say oxygen, the oxidation numbers of oxygen is 2 minus. Am I right? So we assume that oxygen is more electronegative. Not assume, it is more electronegative. So oxygen is supposed to be the negative side. Sulfur here is supposed to be the positive. Okay, because oxygen is more electronegative. But what is the actual oxidation numbers of sulfur? Very simple. If you're looking for sulfur oxygen, you have to make it by default. So what is the common oxidation state of oxygen? -2. So S is unknown, plus with -2 multiplied by 3, because I have 3 oxygen in the molecule, equals to what, guys? SO3 overall, the whole molecule is neutral, no charge at all, so equals to 0. So then you can get sulfur equals to +6. So the oxidation numbers of sulfur in SO3, covalent molecule, is actually +6. You get it? So for simple ion is straightforward. For element is also straightforward. But for covalent molecule, we have to make assumption that the more electronegative atoms or element should carry a negative charge. The more positive or less electronegative should carry a positive charge. All right. So this is how we make assumption to identify the oxidation numbers in covalent molecules. All right. So next one. Now, in a neutral molecule, the sum of the oxidation numbers of all atoms equals to 0. Like I mentioned just now, this whole molecule, there is no charge indicated at the top right corner, right? There's nothing there. So which means it indicates that the charge of the overall compound is equals to 0. But for this, you see that? The whole molecule having a negative charge here. This negative charge is for the whole thing. It's not only for the oxygen. So this negative charge is the overall charge. So when we write the calculation, it is actually equals to -1, not 0. Okay, not 0. If the compound or the ions given is having a charge. So these must you must be careful on that. Just beware of the charge for a mono or polyatomic ions. Okay, so let's do some example. All right, so calculate the oxidation numbers of manganese, Mn, in the following compounds. I have 3 compounds here. Let's do it one by one. MnOH2, right? So again, overall here, what do I see? I see no charge at the top right corner, so which means it is equals to 0. So manganese is what we want. Add up with whatever we have here. I have 2 oxygen. And what is the common oxidation state of oxygen? 2 negative. So 2 multiplied with -2 plus, and then hydrogen. What is the common oxidation state of hydrogen? +1, right? Follow the charge or follow the group numbers. So you have 2 multiplied by 1, +1. And you add up everything should be equals to the overall charge here, which is 0. And then Mn equals to -4 plus 2 equals to 0. Mn equals to +2. See that? -4 plus 2, you get -2, -2, you bring over, you get a +2. So oxidation state of manganese in this case, in this compound, is actually +2. All right, so that's one. And then we have this, MnO4. 2 minus, see that? The top right corner, you're seeing a charge, right? So this is the overall, so equals to -2. And all add up, manganese plus how many oxygen here? 4. 4 times multiply by -2, because that's the common charge of oxygen, equals to -2 overall charge. And what do we get here? Mn is equals to -8 +8 plus 2, so you get so here is negative, so -2 plus 8. Right? So then your manganese is actually equals to +6. So that's the oxidation numbers of manganese. And last one, Mn2O7. What is the top right corner here? Nothing. So it's equals to 0. So don't forget you have a 2 and 7 here. We have to do it. So 2 manganese, which is unknown, plus 7 oxygen, which is minus 2 times 7, equals to 0. So 2Mn equals to positive 14, right? You bring it over, you get positive 14, and then manganese equals to 14 divided by 2, you get positive 7. So that is the oxidation number of manganese in Mn2O7. Now, we can see the example here. Manganese is a metal, and it is from the transition block, right? So we expect the transition metals to have multiple oxidation state. All right. So when they are in different compounds, different mixture of atoms, okay, they have different oxidation state. And this is the proof. Manganese with hydroxide, you get positive 2. Manganese with oxygen alone, all right, you can get a positive 6. Or manganese with 7 oxygen, then you can get a positive 7. So it changes. Okay, so remember these guys. All transition metals can have multiple oxidation state. That's one. Second thing, you may not know this, okay? Elements like phosphorus, sulfur, all right? Elements like phosphorus and sulfur and beyond. Beyond as in after sulfur, we have chlorine, argons, right? Argon is not counted because it's inert. So beyond as in after sulfur, you have chlorine. After chlorine, you're moving on to other period, right? It's period 4, which is the calcium, potassium, period 4. So other than phosphorus, sulfur, chlorine, all right, germanium, arsenic, right, selenium, bromine, all these can have multiple oxidation state. Always remember sulfur, phosphorus, and the elements beyond it after this can have multiple oxidation state. Except, guys, don't confuse this part, except group 1 and group 2. Because group 1, group 2 is always giving you a fixed oxidation numbers, including group 3 for boron and aluminium. Okay, gallium onwards, they might give you different oxidation numbers due to their forming different compounds. So always remember that group 1, group 2, fixed. Group 3, boron and aluminium. The rest, it is possible, which is beyond sulfur. The rest is possible to have a multiple oxidation state. So don't be surprised if you see an element supposed to be group 3 or group 14. It's not a transition metal, but it can have more than one oxidation state. Don't be surprised. It is possible. So anything beyond phosphorus and sulfur, including sulfur and phosphorus, they can have multiple oxidation state. All right. So anything beyond this, including these two, can have multiple oxidation state. Now, since we are talking about redox reactions, right? How do we actually construct a redox equations? Now, to construct a redox equations, you have two ways of doing this. Number one, you can copy the half equations from your data booklet. Because data booklet, there is one page called electropotential difference or electropotential value. So this page, they will give you all the commonly used half equations. Okay, commonly used. So some equations you might not able to find from there, but most of it are there. Okay, so first thing, you just copy from the data booklet. Or in this case, you're supposed to learn how to construct on your own. Okay, now to get the redox equations, we must construct half equations. What is that half equations? Half equation is one stands for oxidations, which involve release of electrons. Another half equation is actually reductions, involve gaining of electrons. So you have to show two half equations before you can get an overall redox reactions or redox equations. Got that? So next, I'm going to show you the example how to come up with your own redox equations, okay, or half equations. Look at the example given here. I have this reaction. Now, this equation not necessarily in a balanced form, doesn't matter. Now, we know that H2O2 and manganate, these two are reacting, undergo in oxidation reactions, and then you produce manganese and oxygen, as well as water. Right? Now, first thing first, you need to write out, split them into two separate equation. Number one, we know that manganate is going to change into manganese, right? Here to here. And obviously H2O2, hydrogen peroxide, is going to change into oxygen because decompositions of H2O2 is changing into oxygens. So you only get one product. What about water? No worries. When we construct the half equations, later we will know where the water comes from. So now assign a product for each of these reactants. So manganese is the product of MnO4. Oxygen is the product for H2O2. Okay, it's quite obvious. All right, and water, later you will know. Okay, one by one, we start out with this. So step one, you see that? I assign oxygen for H2O2. So this is the first step. Done with this, what is the next thing you need to do? Try to balance it. Try to balance whatever you can. All right, now look at this. I have oxygen here, O2. I already have O2 here. So oxygen is balanced. What about hydrogen? I don't have hydrogen, right? So in order to balance the hydrogen, you can add in H plus. Where do the H plus comes from? The H plus is from this. See that? Acidic condition. Acidic condition means you have a lot of H plus, acid, right? So I add H plus on the other side in order to balance it. How many hydrogen on the left? 2. So I need to put 2 hydrogen here. There you go. You get the second step. I got the same equation here. All right. So double check. Do I balance everything? 2 hydrogen on the right, 2 hydrogen on the left, 2 oxygen, 2 oxygen. Yes, it's balanced. So once we have balanced everything, the next thing we need to do is to balance the charge. Okay. Always the last step, to balance the charge. Now, how do we know how to balance the charge? Look, H2O2, what is the overall charge here? 0. Top right corner, nothing. On the product side, oxygen, 0. But here, what about this? H is positive, right? And how many H do I have? 2. So overall charge here is 2 positive on the product side. On the reactant side is 0 overall. Now, to balance the charge means you must make sure that both sides is the same. Now we have positive on the right, 0 on the left. So how do we actually balance it? By adding electrons. Electron is negatively charged. So where should I put the electrons in order to make sure that both sides is actually having the same charge? So I put it on the right. Why is it on the right? Because 2 positive, 2 negative cancel out. So both sides now having 0. And that's how we get the third equation. All right, so this is one of the half equations from these reactions, from the top reactions given. So I have done with one of the half equations. Next thing you need to do before we move on, you need to identify whether this half equation is an oxidation reactions or reductions. And it's actually very simple. If the electron appear on the right-hand side, therefore you're releasing electrons in this reaction. Hence, this is actually an oxidations. All right, so oxidation half equation, done. Next, we move on to MnO4 and Mn2+. So, start up with this, again, step 1. MnO4 minus Mn2+. Now check, manganese, I have 1, Manganese is balanced. But I have 4 oxygen here, nothing. So how to put oxygen in, guys? Water. How many oxygen do we need? 4, right? So put 4 H2O so that I get 4 water. 4 oxygen. All right. And then you will ask again, what if I put water in? I can balance the oxygen. What about the hydrogen? How many hydrogen do I have here? 8. But no hydrogen on the left. Still remember previous one? To balance hydrogen, what do you need to add in? Hydrogen plus, because it's under acidic conditions. So how many hydrogen here? I need to put in 8H plus to balance the hydrogen. So once you put in water to balance the oxygen, you have to put in hydrogen to balance the hydrogen. So make sure everything is balanced. Then we can move on. Now after this, we actually reach to this step. See that? It's the same thing. Step 2. Manganese, Mn2 plus, 4 water, and then moving on by adding 8H plus, you get step 3. So we are done until step 3. So double check. Manganese, I have 1, oxygen 4, because 4 times in, and then 8 hydrogen, 8 hydrogen. So we are done. Last step, what do we need to do? The charge. So what is the charge on the left? I have -1 here. Okay, I have 8 positive, so plus 8. Okay, and then I have 5 negative. No, not this. We are not supposed to follow the step 4. Step 4 is the final answer. We should start from here. Okay, so negative here, I have -1, 8 positive, so plus 8. So what is the overall charge here? -1 plus 8, so you get plus 7. Overall charge is 7 on the left. On the right hand side, 2 plus. Water, neutral, right? No charge on the top right corner, therefore overall charge is plus 2. Now, one is plus 7, one is plus 2. In order to balance the charge, we always add in electrons. The question is, where should I put the electrons in order to make both sides balance? Of course, you put the electrons on the left, because 7 plus 5 electrons, you get 2 plus, which is the same on the right now. So therefore, the electrons appear on the left hand side. So this is the final equation where we have balanced the charge as well as all the elements in it. So what happened now? This equation, these half equations, is actually reductions. Why is it reductions? Because electrons appear on the left. It means you're gaining electrons to form the product. Okay? Electrons on the left, reductions. Electrons on the right, oxidations. Make sense? Now, before we move on to come up with an overall redox equations, I need to conclude something here. Now, to come up with the half equations, like in this case, under acidic conditions, all right, you only can add 3 things. First is water. Second is hydrogen plus, if it is under acidic conditions. Third one is electrons. These are the 3 things that you can add in order to construct a half equations. So water is to balance oxygen, wherever you have oxygen. H plus is to balance, of course, hydrogen. Okay, whenever it is, just put it aside, make sure both sides are balanced. Electron is to balance the charge, overall charge on both sides. So remember this, under acidic condition, these are the 3 things that we should add in. What about under alkaline conditions? Under alkaline condition, then the H plus will turn into OH minus. That's it. Okay, the same thing will happen as long as you have balanced elements, you have balanced compound, you have balanced charge. Then you can get a proper half equations. All right, now, just now we came up with 2 half equations, right? This is the one. All right, now how do we get overall equations? Step 1, you write out the 2 equations, and now you realize that first half equation I have 5 electrons, second half equation I have 2 electrons. Now how do I combine it? Make sure both half equations having the same number of electrons. So how do I do that? First equation times 2, so that I get 10 electrons. Second equation times 5, I get 10 electrons as well. Then you can balance them into these equations. Okay, this is not the final answer yet. Can you see that? I have, this is not H2O2, guys. Sorry, wait. Yeah, it is H2O2, and then 8 water, oxygen, hydrogen. Yes, it is not a final answer yet because I have hydrogen on both sides. You still have to further balance it. So 16 hydrogen on the left, 10 hydrogen on the right. So how to balance it? Take out the 10, here left 6 overall. Therefore, you get a final equations here. So this is your final answer. See that? I only have 6 electrons, 6 hydrogen plus left, because just now we cancel it out. So always cancel out from left and right if you have something similar. All right, so that's how we come up with a redox equation. That's the overall final answer. All right, now after so long, you may be confused now. Oh my God, too many steps, right? So let's give you another example. All right, this is quite simple, in fact. So let's say I give you this Cr2O7, 2 minus, plus Fe2 plus, forming Cr3 plus Fe 3 plus. Okay, again, this equation given is not balanced, not necessarily balanced, because I'm just showing you chromate. Dichromate here is changing into chromium. iron 2 plus here is changing into iron 3 plus. So like the first step that we did, we always assign the product to each of the reactants. And then start from there, we come up with a half equation. So I split the screen into two. First, I'm going to do this. The simple one, right? The simple one is Fe2 plus changing into Fe3 plus. Very simple. Now, first step, what do we do? Balance it. So is it balanced? One iron, one iron. Yes, it's balanced. So nothing else to balance, right? So you don't have to add water, you don't have to add H plus. So what next you need to do? Balance the charge. Also straightforward. Step 2, I'm going to balance the charge. I have 2 plus on the left, 3 plus on the right. So to put in electrons, where should I put in to balance the charge? Fe2 plus, right? Changing into Fe3 plus 1 electron. See that? 3 plus, 1 minus, you get 2 plus, which is the same on the left. So done with the first half equations. Simple, right? And then, let me change color. Next, we're going to change Cr2O7, 2 minus, all right, changes into chromium 3 plus. Step 1, please balance them, all right, step 1. So I have 2 chromium on the left, so I should need 2 chromium on the right. Make sense? And then what about oxygen? I don't have oxygen here, so what do I put in? H2O to balance oxygen. And how many oxygen do I have? 7. Right? Okay, we balanced the oxygen already. And what do we have extra here? Hydrogen. So step 2, balance the hydrogen. So I have Cr2O7, 2 minus, changes into 2 chromium, 3 plus 7 H2O. So how many hydrogens should I put in on the other side in order to balance on both? I have 14 here, so I put 14 H plus. All right, first we balance the chromium. Second, we balance the oxygen by adding water. Next, we put hydrogen plus to balance the hydrogen. So I guess we have balanced everything. Next, we need to balance the charge. Okay, let's check it out, the charge. How do we balance it? What is the total charge on the left? 2 minus 14 positive, right? So 14 positive, 2 minus, okay, plus 12 on the left. And here, 2 times 3, so plus 6. Water is neutral, nothing, so plus 6. Plus 12, plus 6. To balance them, add electrons. That's that. This is the final one when we put in the electrons. Where should I put the electrons in? Electron is negative, so put on the side where you have more positive. So how many electrons should I put in? Cr2O7, 2 minus, plus 14 hydrogen. I put in 6 electrons. Why? Because when I plus 6 E minus, 12 plus 6 E minus, you get plus 6, same. Right? So 6 electrons on the left, forming 2 chromium. Everything should remain unchanged on the right. So now if you double check the charge on both sides, it should be the same as plus 6. So this is the second half equations. All right, so obviously guys, the one on the left, because the electron is on the right hand side, so this is oxidation. And the electron appear to be on the left on this, so this is reduction. Okay, and then that's not the end yet. We have to get the overall redox equations. Allow me to erase that so that I can write it out. Proper one. Okay, I rewrite it, no worries. So Fe2 plus changes into Fe3 plus E, first half equations, and then we have Cr2O7, 2 minus, plus 14 hydrogen, plus 6 electrons, changing into 2Cr3 plus 7 H2O. All right, equation 2. Now, next thing, what would you check? Balance the electrons. I have 1 electrons here, I have 6 electrons here. So how to balance the electrons on both sides, guys? The first equation need to multiply by 6. Then you can cancel the electrons out. See that? 6 electron on the right, 6 electron on the left. No more electrons involved. And the rest, you just put that in. Whatever on the left, you put it on the left. So Cr2O7, 2 minus, plus 6Fe, 2 plus. All right, whatever on the left, plus 14 hydrogen plus, no more, electrons no more. Turn into whatever on the right, just put it in 6Fe3 plus 2Cr3 plus 7H2O. Just copy it down. Once you have balanced the electrons, it's very simple. Now this is the overall redox equations. Okay, I hope you can get that. So this is how we come up with the redox equations. Okay, done with all this basic redox, half equations, oxidation, reductions. Now, what is the applications of electrolysis? Electrolysis can be applied in many industrial processes. All right, and by the way, electrolysis is based on redox reactions. All right, now what is that electrolysis? Why do we need that? Especially important for those industrial that would like to extract metal. Okay, certain metals are very expensive and are rare on Earth. So usually metals are not appear as a pure form. You won't get sodium as a pure form. You won't get iron as a pure form. These are all from the Earth crust where they exist as an ore. For example, iron, we can get it from iron ore, which is iron oxide. All right. Aluminium, we don't have pure aluminium on Earth. We only have aluminium oxide, or we call it as bauxite. All right. The ore of the metal. So how do we actually take or extract the pure metal from the ore? Electrolysis is one of the methods. Okay, although it's straightforward and it's fast, but cost of operation is high. Okay, because we are using power to break down the compounds and back into its elements so that we can remove it by filtrations or yeah. All right, so this electrolysis. Basically, electrolysis is turning electrical energy into chemical energy, which means I'm using electrical energy to break down a compound, to break down a chemicals, okay, back into its element so that I want that elemental state. For example, I want to produce chlorine. Where do I get chlorine from? Sodium chloride. Okay, let's say I want to get oxygen. Where do I get oxygen from? Water, right? Because hydroxide from water, when you decompose by electricity, it will turn into oxygens. I'm sure this one you heard about it, right? So electrolysis basically is to get whatever elemental state that we want, any pure metals or any pure gases. All right. So these are the certain terms that you need to pay attention. Number one, electrolytes. Electrolytes is the solutions with the ionic compound, and it's able to conduct electricity. Why is it conductor of electricity? Because ionic compounds, you have free moving ions. So electrolytes is actually a solution or a molten. Molten means pure liquid. You melt the ionic compound. For example, I have sodium chloride. I don't add water. I don't dissolve it. I just heat it up until it melts into liquid. That's molten compound, which can conduct electricity. All right, electrolytes. Anode. This one sounds familiar, right? And looks familiar as well. Anode. Anode usually oxidations take place, not usually, always. Oxidation take place at the anode. Cathode, reductions take place at the cathode. This is always true. Okay, now what is that anode and cathode again? Anode and cathode is actually a terminal that connected to the power supply, usually a battery. Okay, a positive terminal battery is connecting to the anode, and a negative is connecting to the cathode. All right, so now basic electrolytic cell. Now this is how it looks like. I have electrolytes in the beaker. Okay, and then I have two electrodes here. Anode, see that? Connect to a positive charge of the power supply, and then cathode is connected to a negative charge power supply. And usually these so-called anode and cathode is usually made up of graphite. Now, why graphite? First thing, it is a solid conductor, which means it's in a solid state and it's able to conduct electricity. So graphite is the best because graphite is cheaper than any other conductors, all right? And graphite is inert, all right? So we need inert, we need it to be a solid state, we need it to be a conductor. Now you may ask, what about platinum? Okay, what about palladium? All these are inert metal, but platinum and palladium, obviously, they are more expensive than carbon or graphite. So therefore, most of them, majority, we are using graphite in the electrolytic cell. Okay, now, like I mentioned, during electrolysis, the compound will break down into positive and negative ions because it is an electrolyte, which is an ionic compound. So the positive ion will be attracted to the negative cathode. Obviously, this is negative. So positive ions will be attracted here. Okay, and here is positive electrons. Obviously, the negative ion will be attracted to the anode. And that is why negative ions, also known as anion, because it attracted to anode. And positive ion, also known as cation, because it is attracted to cathode. Now, this is how cation and anions, the terms from. Okay, so they name after the process, the electrolytic process, because the ion moved to different terminal, anode and cathode, so they name after that. Okay, so this is how it looks like for electrolysis. Of course, I'll give you examples of how electrolytics work in the industry. Now, what you can see now is electrolysis of brine using diaphragm cell. Okay, what is brine? Brine is actually usually concentrated salt solutions. Sometimes in industry, they put it as aqueous, okay, like dilute. And sometimes they use molten, and it depends on what you want. But the main purpose of this electrolysis of brine is actually to produce chlorine gas. This is the main product they want. They want to produce chlorine gas. So the best way to produce chlorine gas is electrolysis of sodium chloride salt. First, sodium chloride is cheap and is available, okay? And then from there, we can actually use electricity to break it down, and we can get a chlorine gas at the anode. All right. Now, how does it work? I don't see the need of explaining this, so I will go through it quickly. All right. So this is not molten, guys, concentrated. Usually, all right, concentrated. So what will happen here if you have concentrated NaCl? In the diagrams, they miss out certain things because they put molten. So I should have OH minus and H plus. Where does this come from? From water. But these two will have low concentration, because they say concentrated NaCl, so which means I have high concentration of sodium and chloride. Now, what happened when electrolysis takes place? So battery connected to the graphite, and what happened? The negative ions, which is OH and Cl minus, both attracted to the anode, and sodium plus with H plus both attracted to the cathode. But will both actually discharge? Which one actually undergoes reduction for sodium plus or H plus? Which one will reduce? Because we are breaking it down into elemental state. When they are at the cathode, see that electrons are coming in. So cathode is actually a provider of electrons. So when positive ion attracted to it, it will accept the electrons from the cathode and changing it back into a neutral element. Okay, they will accept electrons from here, but the electron will go to sodium or hydrogen. This you have to base on reactivity series. So H plus is much all the way down. Sodium is much more reactive. So which one do you think they can accept electrons willingly? Okay, they're willing to accept electrons and change into neutral. Of course, hydrogen. Because hydrogen plus is less reactive. So it may change back into elemental state. Sodium is more reactive. So sodium will stay as sodium ions. Right? What about chlorides and hydroxide, Cl minus and OH minus? Now, obviously, we usually choose OH minus. All right, but in this case, due to the low concentration of OH, then chloride will be the one that chosen to be discharged due to high concentration. It is slightly different from sodium and hydrogen because sodium is also at high concentration, but the reactivity difference between sodium and H plus is too big. So they will still choose hydrogen to be discharged. So hydrogen gas will be given off by accepting electrons to form H2 gas. In this case, due to higher concentration of chlorine, therefore chloride will actually release electrons to form chlorine gas by releasing 2 electrons. And these 2 electrons going up through the battery, replenish, and the 2 electrons will come over here. So they are replenishing the electrons. First, the negative will provide electrons, and here we have empty electrons. Due to potential difference, the electron release here will be pulled up and replenish whatever electrons losing out. Okay, so this is how the whole process works. So now I'm getting hydrogen gas as the main product, like I mentioned, and hydrogen gas as a byproduct. We don't need that, but that's the bonus. Okay, we get hydrogen gas at the same time when we are producing chlorine gas. So that's what we call a byproduct, which is not what we are looking for, but yeah, it produces together as the main product. So this is what I explained just now. Oxidation happened at the anode, reduction happened at the cathode, and when you combine these two equations together, half equation, like what I did just now, you get an overall redox reactions or equation. See that? This is the main product, and that will be a byproduct, which we don't need it, but yeah, as a bonus. See that? And here, you see that at cathode, I still have NaOH being produced. Where does the NaOH come from? Come back to this. Just now, H plus is being discharged, right? Discharge means you change into neutral. So H plus gone, forming hydrogen gas. Chlorine gone, forming chlorine gas. And what left in the solution? Na and OH minus. So in the solution is the remaining sodium hydroxide. So the solution here is a basic solution, which is highly corrosive. So a special care or a special treatment needed for this process. After you get a chlorine gas, you need to do some pre-treatments to the sodium hydroxide because it's highly corrosive in the industrial. All right. So that's why NaOH is another byproduct. All right, let's move on. Now, this is the last part of your electrochem. We are not learning electrolytics now in a way because electrolytics, we will learn it again in SEM 3. Yeah, so SEM 1, we're trying to grab all those basic before we can move on to something more advanced. So the last part of this topic is factors affecting the amount of substance liberated during electrolysis. We have been talking about electrolysis, we have been talking about producing chlorine gas, producing the metal that we want, trying to break it down and try to get a pure metals, right? Now, how do we determine the amount of substance produced? Like just now, what is the mole or what is the concentration of chlorine gas produced since this is a main product? So how do we know how much chlorine gas is actually produced? Okay, how do we do or perform a calculations for that? So it based on this, Faraday's first law of electrolysis. Now, it is not unfamiliar to say Faraday's law. You learn that in physics, all right? So it states that the mass, it can be a mass of gas or solid, the mass substance produced at the electrode, it can be anode or cathode, during electrolysis is directly proportional to the quantity of electricity through the electrolytes. What does that mean by quantity of electricity? The total charge that passed through the cell or the electrolytes will directly affect the amount of main product or byproduct, or generally will directly affect the products produced at the end of this electrolysis. Okay, so quantity of electricity or charge is the main key. Okay, and there's one relationship here stated by Faraday's first law. 1 Faraday, 1 F, is equivalent to 1 mole of electrons, which is equivalent to this 96500 Coulomb charge. This is the charge for 1 mole of electrons. You see, 1 mole of electrons, how many electrons there? If we count individually one by one, 1 mole of electron equals to 6.02 times 10 to the power of 23 electrons, right? And total electrons will give you this charge, 96500 Coulomb charge. So if you have 1 mole of electron flowing through the electrolytes, the total charge or the quantity of electricity passing through it is equivalent to 96500 Coulomb charge. That is what we call a Faraday constant. All right. And what is the relationship between Faraday constant and Avogadro constant? Still remember just now I showed you the Avogadro constant here, right? So the relationship between them is Faraday equals to Avogadro constant multiplied with E. E is actually the charge of one single electrons. The charge of one single electrons multiplied with Avogadro constant, you will get your Faraday constant, which is almost 96500 Coulomb charge. Now, this value is sometimes deviate slightly. Why? Because of the conditions, the temperature, the pressure, and because electrolysis can be at high temperature, it can be at high pressure. It depends on what process or what products you are aiming to get, right? So these could be deviates a bit, but most commonly constant used for Faraday constant is 96500. You may actually see this value as different constant in physics, but doesn't matter. In chem, this is the standard value, and this value is actually given in your data booklet. All right. So basically, Faraday constant, how you get 96500, you just need to multiply Avogadro constant with the charge of a single electrons, you will get 96500. That's the relationship, all right? But that's not the all of it. Now, this is how we perform our calculations. It's quite standard. I show you the step. So every single time when you deal with these equations or deal with these kind of questions, you follow the same step, whether going forward or backward, you should be able to get the answer. It's very simple, okay? Now, let's look at this. Calculate the mass of silver deposited at the cathode when a current of 0.5 A is passed through a solution of silver nitrate. Now, silver nitrate is an electrolyte because, yeah, free moving ions, right? For how long? 15 minutes. Now, these are the information. 0.5 A, 15 minutes, asking you for the mass of silver deposited at the cathode. All right. Now, first, that one. We always use this. Q equals to IT. Looks familiar, right? This is to calculate the charge or the quantity of electricity. All right. So Q equals to I, which is 0.5. T here is 15 minutes. So T is actually in seconds. Okay. So 15 times 60. 15 minutes times 60, convert it into seconds, you get 450 here. 900 times 0.5. All right, so this is Coulomb charge. First step, I got the charge. This is the total charge passing through the electrolytes for 15 minutes. All right, step 2. Still remember just now I said 1 Faraday constant equals to 1 mole of electrons. And 1F is actually 96500 equals to 1 mole of electrons. This is a Coulomb charge. See that? Now, since 96500 producing 1 mole of electrons, produced by 1 mole of electrons. So how many mole of electrons if it is just 450? All right, so the solve the equations here. So it's just 450 over 96500 equals to the mole of electrons, which is equals to 4.7 times 10 to the power of negative 3. That's the mole of electrons. That's step 2, right? Step 3. So step 3, what they are looking for, mass of silver. So we need to write out the half equations for the reductions of silver ions because initially we are using silver nitrate, which is silver plus. NO3 minus. So we are changing Ag plus into Ag solid. So this is a reduction. So we need to write the equations out. Okay, so from silver plus E, you're getting silver solid. Balance? Yes. All right, in terms of charge, in terms of element. So we have this amount of mole for electrons. So we can put it in. What is the ratio of electrons to silver? 1 to 1. So I expect the same mole for silver, 4.7 times 10 to the power negative 3 moles of silver. Boom, right? 1 to 1 ratio. And what is the mass? Just use the mole. Okay, 4.7 times 10 to the power of negative 3 multiplied with the molar mass of silver. So what is the molar mass of silver? 108. So times it with 108, you will get the mass of silver deposited is 0.508 grams. There you go. That's the final answer. Now, same question here. They might change it into different metals. They can change it into copper. Silver is plus, copper is 2 plus. So the equation is important, the ratio. But step 1 to 3, all this that I show you just now, they're going to be used for the same questions. I mean, for the same type of questions. So just follow these 3 steps. Sometimes they might actually change this. Just now they're asking for mass, right? Sometimes they give you the mass, they give everything, ask you to look for the time taken. So you have to calculate from here all the way backward in order to get the time. So they can make anything unknown in between, but the step will be the same. 1, 2, 3, that's it. All right, I guess that's all for this topic, the constructing redox equations. What is redox? Calculating oxidation numbers, half equations, what is electrolysis, how electrolysis work, how to perform calculations in order to identify or to determine the amount of products at the end of the electrolysis. So these are the main thing. And we have achieved all the learning outcomes, I guess, if you check back. All right, thank you for watching. Tutorial video will be up soon.